Hi, I'm Tom and I talk about code. Welcome to another Rust programming live stream. Today, another step in my compiler, a very important one. We're going to be doing string literals. What are string literals? String literals are things that look like this, surrounded by double quotes, some series of characters. Super Cricket, welcome. Good morning. Good morning. Thanks for coming by. So we're going to do this. For this, we need to write a parser. We need to work out how we actually store static data, because this is going to be data that gets defined at some point, stored somewhere, and then we don't change it again. This is part of, the blob of data that gets loaded along with this binary that isn't actually code. And basically, as we do this, we're going to get closer to this overarching question of how do we load a binary? What does it mean to load a binary? We might actually have to define a binary format as part of this. We might end up going on a side quest. So binary and this would actually be good, kind of, because at the moment the way I pass symbols around, kind of debug data is very, very jank. So it would be nice if I could have a binary blob that just kind of came with some of that data. Might be useful. But now that I'm running this in the way, and escape characters as well, this is a bit of a question. Recursive descent is going to make it really easy to do this part, but if I want to have, for example, a string that looks like this, which would be very valid in other languages, where we would say maybe foo bar, and you have a quote character escaped in the middle, this is a bit more complicated. Little tiny bit more complicated, because, well, and with this become apparent as we write our parser. So this would be fun to tackle as well, and then if we get that done, we're going to work on the WASM build for our compiler, because it currently doesn't work. If I try and build for WASM, it yells at me because we use the RNG crate, which isn't supported in WASM. So we're going to have to do our own random number generator. And we can do that. That's not too hard. So this all feels pretty approachable. We'll see how much of it we get done in one stream. Would be nice if we can get it all done in one stream. That'd be pretty cool. So let's go in. Let's start in AST, as we always tend to do. And, well, we have a car type, we have a pointer type. What is a string? What is a string? This is another quick important thing, right? What's the type of this? Would anyone care to guess? Would anyone care to guess the type of a string of characters? While I just quietly ban a guy from my chat. The type of this is obviously going to be pointer to car, right? These characters are going to get shoved into memory somewhere, and when we reference them, we do it by a pointer. Awesome. Hopefully that'll be pretty simple. So we don't have to do anything in the type world. We don't have a string type, but string type is just an alias. It's just a name for a pointer to a character. And we're going to have an expression type, and we're going to have an expression type that is a literal string. Just like this. Any valid Rust string is going to be fine here. Now, actually, probably not. Now, there's a type, right? There's a Rust type for, and let's do this in the actual Rust docs. There's a Rust type for like strings, for ASCII strings. I think C-stir. Borrowed C string. Or maybe I just want a slice of car, right? Or an array of car. Right? But I want maybe not an actual string. For now, let's just say string. Let's just say string and assume that just because it looks simpler. But realistically, we don't want UTF-8 here. I guess there's nothing wrong with having UTF-8, but the way we're going to draw strings, the way I'm going to do tiled font rendering, UTF-8 won't really make much sense. But I guess that's not the end of the world. So we have a literal string, and when this gets printed out, S, we're going to write similarly to the car, and interestingly here, we have to use these escape characters, right? Because a string is delimited by these double quotes, so if you want a double quote inside your string, you have to put a slash before it. That stops it from ending the string. So with that recursive descent parser, this is actually going to be hard to do, but a string like this is going to be fine, and we're going to see this. Where else does this break? This is going to break when we compile. That's good. Is that it? Yeah, okay, so we probably will actually do this, right? Literal int, literal car. let's do AST expression literal string. And this is just something that we haven't implemented yet. So we put a to-do here just so that we can build and keep going. This is like a little hole that we're going to come and fill in later. And yeah, we don't want to actually use the type. Okay, where else haven't we used it? We've got a question in chat that I get quite a bit. And I like talking about this. I love talking about this. So, what is this? Get out of here. Get out of here, Apple. I don't want to see it. Steve Jobs, get out of here. Igris GG, welcome. The YouTube algorithm recommended me. You're curious how I code without code completion or some kind of linter and formatter. Well, without code completion, it's just because it's a 3,000 line code base. I kind of have it all in my head. As far as the Rust stuff goes, I just frequently refer to the docs, which is really useful. It's a good way to work. As far as linter and formatter, I have that. I have cargo format. And actually, when I try and commit code, it won't commit if cargo format hasn't been run. I also have cargo clippy as a style guide. They just don't run automatically when I like save files, because I don't like moving stuff around unless I explicitly ask for them to move around. So that is my simple take on why I do that. I love talking about it. I love that people are really really passionate about this. Okay, so a literal string is going to have type. It's a pointer that is a box, a pointer that points to a car. And that should be good. Beautiful. Okay, so we can build that. We can build code where there's a string in the AST. It crashes if we try and use it, and we don't actually parse it. So the next logical step is to add a parser in our language. And this file really needs to get split up as well, because this 700-line monstrosity is pretty gross. I have been reading a few of the things that people have recommended, like with, I think they're called left subtree recursion elimination. I'm going to try and do that and make my parser better. Also, operator precedence. The VM actually supports more operations now. It supports all the bitwise and or EXOR. I also added mod, so operator precedence is going to become more important. Where do I want to do this? Literal. So I'll put this with my other literals. Literal base 16, literal car. So we want a function expression, literal string. We're going to take an input. We're going to give back our result type. This is a result that has confidence, where we add extra information to the compiler so that it can work out how confident it is about this being the main cause of the problem. For example, if we're parsing a string, if we've already seen our first double quote character, we're probably actually fairly confident that this is related to string parsing, so we might say that this is high confidence. We might say that it's high confidence. So we're going to map. We're going to map whatever we can get through here, whatever we can get wrapped in double quotes. And we're going to take as many as we can, right? So we're going to, with confidence, we're going to repeat at least one time the not car. So anything that isn't another double quote, we're going to try and take at least one of those for this to succeed. Actually, no, we're going to try and take at least 0 because empty string is a valid string. Cool. And we're going to say confidence medium. We have low, medium, and high confidence. Cool. So this has to be wrapped up in double quotes itself. And we stop looking when we find a double quote to try and then find the one at the end. That all sounds good. Cool. And we're going to map this into... now, this isn't quite as simple, is it? It's got to be x dot... This is going to be a vec, I think. Yeah, we're going to get a vec of t. So can we go... I want a rust vec of car vec of, yeah, car into string. There's got to be a way to do this conversion. I just can never remember what it is. And someone, oh, actually, that's beautiful. That's beautiful. Into iter collect. Too excellent. And we just pass the input into that, and that's our response. Okay, it's never used. It's never used. Now we have to copy this. We have to copy it. We have to copy it because we forgot a comma. We have to copy it because we have two different expression parsers because arrays are hard. Okay, cool. So now let's write a test. Let's write a test. Let's go. Test. I really need to split this gigantic file up. It's getting very unmanageable. And we're going to do the same thing we always do, which is make an expected case, try to do the expected case, and do it inside this block so we can reuse variable names. Cool, so this is going to be foo bar baz. We're going to say, we're just going to try and parse it as an expression and see what happens. And that looks good. That's pretty happy. I'm pretty happy with this. I'm pretty happy with this. So let's go into my favorite example file, test.code, and let's say let tt equal foo bar. Okay, what happens when I try and compile this now? And it should fail. It should fail, but let's just see what happens. Excellent. It says that literal string is unimplemented. That's perfect. That's exactly what we want to see, because that's what we've told our compiler to do. Cool, to do unimplemented. So when we see a string, we got to do something with it, okay? Now, what do we do about a string? Let's head back over quickly to my drawing page, okay? Parser, we've done it. We've done it. We're going to check it off. I'm going to do it. Check. Okay, so let's talk about static data real quick. Okay, at the moment, the memory layout for my program looks like this. Okay, you have the start of memory up here. You have, like, let's say the end of memory down here. These are globals, global data. And then this is the program, the actual instructions of the program that get executed, and then the stack is going to be somewhere down here. Weirdly, the stack grows down, and really the stack should grow up towards the program. That would be more correct. I don't know why I made the stack backwards, but that's okay. I just have to deal with the mental overhead of dealing with that at some point. And not get too excited about, oh my gosh, sorry. I keep holding control while I move the mouse. I think, control middle mouse. I don't know, I'm doing some weird zoom stuff here. It's very fun. So, where does a string live, right? What does it mean when we say x equals foo bar? Well, we know all of these strings at compile time, right? They all exist at compile time. We know 100% of these strings. So what we're really saying is x equals the address of some constant data of some, right? So what it's kind of like saying is, well, what if we put this string up here with the globals, and then when we need x, we can just refer to this address. And hopefully this will never change. We can't actually enforce that it won't change, but hopefully it's never going to change. If we know they don't change, then we can do something cool, like every time we have a string foo bar, it can actually point to the same block of memory. Now, because we can't assert that it won't change, I don't know if we can really make that optimization. So I think for every string, we're going to do a thing. I think you could call this interning. You could maybe call this. Yeah, in computer science, string interning is a method of storing only one copy of each string value, which must be immutable. So it's like saying, hey, we're going to put all these somewhere and then, reference only the ones we need. We're not going to double up. We're going to double up because my approach to this compiler has been to do the dumbest thing possible as a first step. The dumbest thing possible is to put every string literal we see into memory, unless it's the empty string. But even the empty string has to... Well, no, the empty string's just null, right? No, the empty string... This is another interesting thing, right? Because if we do the classic C thing, then a string is these bytes, and then in this position here, we've got this sneaky extra thing. I'm going to do this in red because it's really sneaky. It's really, really sneaky. We have a byte 0, right? The 0 byte. 0 tells us it's the end of a string. Okay, so what is empty string? Well, empty string is a string where if you try and get the thing in it, you're always going to see the 0 byte. So I don't know if we can really say that it's null. The semantics of that are not so simple. Maybe it would be good to have a smarter string type where we actually know the length. Maybe we could do that. Maybe we could do that. What would that look like? What would that look like, right? So because again, we know at compile time the length of this thing. I guess what we could do, so we can count this, right? So 1, 2, 3, 4, 5, 6, 7. 7 things in this string. So what if we could store this as a pointer and the number 7, right? In some kind of struct. That would be good. So when we say x equals foo bar, what we're really saying is x equals pointer to this string and the length of the string. And then anything that operates on a string would expect to get both a pointer and a length. Can we do that? It's harder making struct... Well, no, we can make struct literals on the stack. We can do that. All right, let's try it. Let's see what it looks like. So, the first thing we need to know is... We want to put this in a variable. How long is the string? Let's actually show you the code I'm writing. That's better, isn't it? It's a little better. So we want the length of the string. And actually, I don't think it's worth putting that in a variable. But we need to think about it. We need to think about the length of the string. We need to say that ultimately, this is going to be the same as... this is hard because... This is hard because it's no longer an expression that evaluates to one thing nicely, right? When it's just, because this is an expression, not a statement, it has to evaluate to one value and one value only. That's how my language works. If we say that this is just a pointer to a string, then that's fine. We could say that it's a pointer to some arbitrary struct, right? We could say that it's essentially a void pointer, and we're going to try and assign it to something that is a string. Maybe that works. Maybe that would work. So maybe the return is a void pointer, and maybe the thing that this points to, maybe in the global data we need to put the entire structure, the number and the string. And that might actually work. We just put the number first. We just put the length of the string first. That actually would work, funnily enough. So, let's say... let's make a vec called const data. Okay, I'm gonna put it on the screen as I type it. That's usually helpful to the people who are here to watch me code. Okay, I know there's some people who just come to watch me draw, but I do have to show code sometimes as well. So we're gonna make this variable called const data. Okay, the first thing we're gonna put in here, const data, and actually we're gonna be explicit about what kind of vec this is. It's gonna be a vec of U16. No, it's not. It's going to be a vec of U8. Okay? So we're going to grab the length of the string in a variable. I know I said I didn't need this, but now that this is a vec 8, I kind of do need this. I kind of do need it. Because the first thing we want to push, right? The first byte in this thing, because it's the little end of the vec, we're going to push str, len, and hex ff. We're going to push the bottom byte of this. And then we're going to push strlen. We're going to push the upper byte of this, shifted in by 8. So the first byte and then the second byte. We're going to push them in. Then for car in, then maybe we'll say const data.extend s.cars.collect. Is this going to work? Let's try it. Let's try it. Then we have a bunch of constant data, okay? A bunch of constant data. We need to put this somewhere. So let's have a look at the compile context. What does the context have in it? The context has this set of globals. Now, what is a global? A global is an address and a variable type. Address and a variable type. We have this global base. No, we want global head. Okay, so let's say pub fn define static. And we want to make a static thing that is arbitrarily big. So we want to say we need a mutable reference to ourselves. We need... do we need a name for this thing? I don't think we actually do need a name for this thing. We just want... I guess it's not really definition. Let's call it define static data for now. And let's give it... It's just going to take in a bunch of data, right? It's going to take in a vec of U8s. Just random data. And it's going to give us back an address maybe, or maybe not. Maybe we need to grab that first. Maybe we'll say push static data, right? And so then the problem is, again, the problem is when we write this stuff out, oh dear. This also is going to really break, it's going to break the output format where I have this like -a, where I have this dash, where I have this, what is going on here? -a that outputs assembly. Not that I can show it in the current state, but it outputs the actual assembly instructions. That's going to be a problem. So this kind of needs to be a vec, and it probably needs to be called something else. Or, actually, do you know what's better? I stop trying to shoehorn two things together. I say pub static data. And this is a vec. It's a vec of vec U8s. I think that's okay. Maybe it's just like let's give it a U size as well, right? Because, or a U32. We'll go U size because that's what I've done elsewhere. So it's a list of things that are data that we know lives at a certain address. This is the underlying premise of static data, right? Maybe in an ideal world you'd give it some kind of like segment as well, some kind of thing that it's offset from, but for now, just a size, just some data. When we push static data, what we're gonna do is we also need to track the head. We need a static head. Okay, so we need to get something back. We need to give something back from this that we can reference later. So we need to give back. It's going to be a U32. It's going to be the address in memory that this lives at. Perhaps even just a U16 actually. That's good. It'll be a U32. It'll be a U32. That makes more sense. That probably makes more sense. So we push static data. We just need to do this thing. We're going to say let offset equals self.static head. We're going to move it by the size of data. Each element in data is 1 byte, so it's just data length. And then we're going to say self.static data.push. And all we push is the offset of that data. which can be recalculated, but we're gonna push it as well just for it feels a bit safer. And actually, we're just gonna put the data in here as well because we take ownership of it when we push it in. We never need to reference it again. Sigo null, not super late. You're not super late, but it's about 11 p.m. here, so it's getting on a little bit in my time. My energy is level. It's been higher. But yeah, I hope you're doing well. I've had a big day. I watched Twisters today, the dumb tornado movie. It was actually very good. It had no right to be so good. It was somewhat shocking. You go in expecting a dumb tornado movie, and then it actually like had characters and emotions. It was incredible. Highly rate it. Highly rate it. If anyone watching this in the future has opinions on the movie Twisters, I'd love to see them in chat. In a fun YouTube comment. Okay, so we're going to give this back as a U32. This is a bit jank, but we're just going to roll with it. My typing of addresses here is a little bit of a problem. I always forget this. I always forget how you need to deal with the turbofish. Okay, so strlen is too big for this. However, I know that once we've ANDed it with hexFF, it's just going to be a byte. Similarly here, we're just going to wrap this all up as U8. That's better. That is better. Okay, so we didn't get a result here. So we've got our data, right? We've got our vec of U8. What do we do with it? Well, we say context, define, static. We say push. We say push static data. Right, so the static data, and this is just our const data, right? The actual data of the string prefixed by 16 bits of length. We can make a struct, right? So we're going to give this back as a void pointer and then cast this into a struct, I hope. Can I cast between pointer types? If I can't, I'm going to add code to do that. I don't think that'll be very hard. So we've got an address, and every string we see, it's going to get a unique address in our static memory space, right? It kind of has to. It kind of has to. If the string has 0 length, what do we do? If the string has 0 length, do we really just put the number 0? Yeah, we're going to do the simple thing. We're going to do the simple thing. We're not going to use null to mean empty string, okay? We're going to keep null as its own special thing. And we're going to try and minimize the semantics of null. We're going to try and not give null special meanings where possible. Null will just be a bad value that shouldn't happen. Okay, so address. All we need now is the actual code that will load that address. And that's all we need to do. Load, we need to go into util because I believe, not that util, codegen util, load address to this function. And it gives us back, so we need to wrap this in an okay. Load address to, we take an address, a target register, and a page register. Adder, target register is going to register C, and the page register is going to register M. Except we need another instruction as well. It's not enough to just do this. We also need to then say out.push. We just need to push. We just need this. Push C to the stack, because we always have to push everything to the stack all the time because I have no register planning in this language. Okay, and then we just say okay out. Perfect. Now I've cast this to a U32 and then back to a U size, but ultimately this should be a U32 everywhere, I think. Constant extend. Extend. No extend. No extend. Why haven't I got extend? What's extend? Vec. Is it not called extend? Extend. Extend. When don't we have extend? Allocator. What? What? Cars. Do I annotate collect? Do I say collect vec u8 expressions must be enclosed in braces to be used as const generic arguments? No, that's not right. No. Oh. They actually must be enclosed in braces. Field expression. Can it be built from? Okay, so we can't convert it. Oh wait, there must actually just be a function in string for this, right? There must be. And I'm just going to search string for it first before I go to Stack Overflow. I'm going to look for vec u8 as from into bytes. There is literally a method for this. Into bytes. Now, there are some problems with this, with length and stuff, but is there an ASCII string type? ASCII. Okay, this is playing with fire, but I'll make it to do. That's okay. Danger UTF-8 plus Sterlen. Okay, beautiful. Into bytes. S moved in this method call. That should be okay. Receiver moves F, moves S. Clone into bytes. Context is behind a. See, previously to this, context did not need to be mutable inside of an expression. But now, because we might encounter a string that needs defining, we have to be able, well, that needs interning. Interning is the wrong word, but we need to do something with that string data. It doesn't actually exist as part of this expression. It lives in a static place in memory. This now needs to be mutable, and this is going to break a lot of things. This is going to be a borrow checker snafu, I think. Maybe not, actually. So S. Why can't we take ownership of S here? We don't actually use S again anywhere. What if I say let... Can I do this? I know sometimes putting things inside extend is a little bit funky. Copy. S is behind a shift. Oh, that's right, because of how we're matching on this. Okay, no, that's fine, that's fine. So, is there a method on string? It has to be a mutable ref. Alright, let's clone it and then into bytes it, which is really silly, but that's okay. I guess it kind of makes sense, right? And then we pass ownership in, so that, you know, something does actually have to do this. I wanted static head, not static offset. I just had offset on the brain. Okay, so I can compile this now, and it should work. It's gonna spit out essentially garbage, but it's gonna work. Cool. So. Now comes the fun part. We have to do something with all this static data. We have to do something with it. So if we look at code gen, top level, cool. For every global, we're going to define a global. Actually, this still doesn't work. The problem is that I'm thinking about this like I'm going to put globals and constants and like static data like strings in this same little section. And that's okay, but the problem with this is that currently I have a global head and a static data head, and these move independently. They don't look at each other. So that means that we're essentially, the first global we define is at address 0. The first static data we define is also at address 0. They can't both be at address 0. That's just not correct. That's just not how things are done out here. So how do we fix this? We make instead of global head and static head, we just call it, let's just use global head. Let's just use global head, okay? So if I build this now, it's gonna say, hey, what the hell? Static head doesn't exist anymore. So we're gonna use global head for this. I'm gonna say global data.len if self.global head mod 2 equals 1, then self.global head plus equals 1, right? So just make sure it's even, because we want things to be nice and even. We don't want these weird, we don't want 16-bit words starting on an odd boundary. That's not cool. Static data push, then we push the offset. And now this is why we stored the offset as well. Beautiful. Beautiful. Okay, now the way we do this is no longer going to work. Oh, yes it is. Yes it is. Globals. Okay, where do we do globals? Globals. Where are these used? Top level? It's not top level though. Is it in here? Global? Where do we, what happens? We come through here, program, compile program. If we're going for, where's get instructions, map error, get instructions. Oh, right, because as far as globals are concerned, we just, as far as globals are concerned, we just don't put anything there, right? Because we initialize them at runtime. But statics don't get initialized at runtime. Statics are initialized at static time. They're initialized at compile time. This is actually kind of a big deal. Kind of a huge deal. So what, compile mod, codegen mod, top level compile. What does compile give back? It gives back a context. Okay, here we go. So we need to pad enough space for the static data, then we need to iterate over any static data we have and actually emplace it. So let's wrap this in a result just in case. It's gonna be a result with it's gonna have a U32, which is gonna be our memory offset. Is it? Oh, this is a bit weird. Let's give it a U size, which is our memory offset, and then a vec of U8, which are just the bytes that need to go out, and it's also going to optionally give back a compiler error. Let's see how this API goes, right? We're giving back the static data for the stuff that we've compiled. So let mut out equals vec new. We're going to concatenate all of these vecs together. We're gonna hold on, what's the API for pre-allocating a vec? We're gonna make one that is exactly as large as we need it to be, and then we're gonna copy things into it. Vec I think it's with capacity, right? With capacity, yes. Okay, so we're gonna with capacity, and this capacity is going to be self dot global head, right? Enough room for every piece of static data we've allocated, because globals and statics both share this global head, so we have enough space. We know we have enough space to emplace anything. Is there extend from slice, extend from within? I would love to be able to copy in at an offset. Can I say rust vec copy at offset? That's not what I want. How do I copy one buffer into another buffer with an offset? Here we go. No, not quite what I want either. Explicitly copy a vector. Dot clone. Okay, so copy is a bit of a loaded word here. It has a couple of different things, different meanings. So we've got a vector that's big enough. Then we're going to loop over for each data in self dot statics. Okay, let's just do the simple loop. For every piece of data, we're gonna say out offset plus id in data dot iter dot enumerate offset plus I equals d. We're just going to write it like this, the old-fashioned way, the old imperative loop way. There's a smarter way in Rust, I'm sure. We're just going to do the simple thing. We're going to do the simple thing. And then we're going to give back, okay, the offset is going to be 0, and it's whatever data we collected along the way. All right, they're not called statics, they're called static data. Nice, nice. Now, for some reason, we have, oh, it's because I need to deref. I need to tell it, don't get a ref. Don't get a ref. We can borrow here, but don't get a ref to a U8. That doesn't make any sense. Just copy the U8. Just copy the U8. Okay, so we're going to go into main. We're going to go into bin lang.rs. This is good. Now. We're just going to unwrap this error where we can, honestly. I don't know if we're allowed to. Let's just unwrap. Let's just unwrap, because this actually should never error. Now. Is this correct? Is this correct? What do I get instructions? What happens to the offset? I don't think the offset really gets factored in here. And I guess that makes sense. Like, if you have an offset of 100, you don't want to have 100 bytes. So this is why we really, really, really want a binary format. So for now, we're going to make our output. It's going to be with capacity. The capacity is going to be instructions.len. For each instruction, we're going to have 2 bytes plus our static data.len. All right, so enough room for everything. Now with capacity, is with capacity what I want? Capacity doesn't mean size. Reserve. Okay. Okay. Capacity doesn't mean size. This is you can use the vec macro for this. Okay. I actually want the vec macro for this. I don't want with capacity. I want the vec macro. 0 initialized with enough data for this. Same thing here. I don't actually want capacity, right? Because capacity is tricky. Capacity is tricky. If you're not careful with capacity, it'll bite your head off. Capacity just means how many things, how much memory is set in place. It still has 0 length. Still has no length, just has capacity. So we have output, and all of these instructions, instead of pushing, we're gonna grab, so let's say offset is gonna be, it's not the static offset, it's the let's just say static data len plus we're going to enumerate this too. Enumerate's pretty good. Wherever the static data ended plus the index of this instruction times 2. Right, so now it's going to be output offset, and then this is going to be output offset plus 1. Excellent. Beautiful. So now what's the other thing? Well, we need to put all of this static data in somehow. So we need to say output dot, I don't know how to do it. I don't know. There's a Rust function for this, and I just can't think of what it is. We'll say id in static data dot iter dot. Cool. So for each bit of static data, again, we're going to do the same thing. We're going to say output I equals d. So we're going to write this entire static section. Okay, now what happens when I build this? It's probably going to be something wrong, right? Yeah, of course. Instructions, I forgot a plural. Expected function found U8. Oh yeah, we can get rid of one set of parentheses here, because this isn't a function call anymore, obviously. This is a array assignment. Expected U8 found U size. That's because this needs to be a semicolon, right? If you have a U size on the right, it's the length. Static offset. Okay, we don't use the offset. Nice. Now what happens when I build this? Well, it doesn't really make a difference here, but what happens when I build this? Now, this is cool. We can see in the binary, well, apart from some garbage at the top, we see we actually have our string foobar, okay? And that comes out here. Foo, is that it? No, that can't be right. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh yeah, see, 2-0, that's a space. Weirdly, we have this 0 byte of padding, and what's this number? What's this? What's going on here? A7. What's A7? That doesn't feel right either. We would expect it to be the, oh no, 7, hold on, 7. FOO space BAR, 1, 2, 3, 4, 5, 6, 7. This is a 16-bit length. So what's happening here is this is not 16-bit aligned. And this isn't 16-bit aligned because there's just some garbage in the output first. So let's find all our printlns and let's get rid of them. Let's make a println hit list. Source bin lang. These ones are pretty important. Compile block, code gen expression. Okay, so that's okay. That's okay. Just gonna get rid of all these. Code gen expression. Actually, let's keep that because that's a weird error thing. And then there's one for local variables as well. Like usage, declare local, compile block. Actually, we can just get rid of that. Okay, so now if I run this, the actual code, sorry, we see that we have a 16-bit number, the number 7, then our string, then some stuff, and then our assembly starts. That looks pretty good. That looks fantastic. That looks really great. So can we load this? Maybe not. maybe we can't quite load it yet. I'm not certain what happens if we try and load this. Because we don't have a way of communicating the offset back to the machine, right? And we probably can do that. So what if I go in just to our test harness, right? Lang test common. Where do we set the program counter? We set the stack pointer. Set PC, program start offset. Okay. Now that apparently is actually set in here. Offset plus global page size. Global page size. Now this is actually not quite correct, right? But we can't work this out. Okay, does anything depend on program start offset? I need to remember this. Program start offset. This is used... No. No, it isn't. So why isn't this used? Program offset. Oh, this is calculated here as well. So we need to know, this is the chicken and the egg problem. We need to know how much static data so that we can work out what our global page, what our global, how big this is, right? We need to work out how big this thing is. But we don't know how big this thing is until we've compiled our program, because there might be strings in our program. So that's a little bit of a problem. That's a little bit of a chicken and egg problem. And that's a problem that's a little bit too big to unpack right now. I can feel my energy level crashing. There is a solution to this. There is a solution to this. The solution is either work through ahead of time and resolve all of our strings into here so we know how big this is, or write code that's resilient to a different starting offset, right? Calculate our function addresses. Actually, no, well, we don't need to know our function addresses, right? Register labels, program offset. We don't actually need to know this here. We could just do another pass where we go through function names, I think. Because the only thing that uses absolute addresses, the only thing that does global jumps, are function calls, and functions are based on symbols. So we can actually do this. What we can do, instead of what we currently do, we can build a new system where, and I'm going to draw this out now so that I kind of remember what I'm thinking, because then I can look at it tomorrow and I'll be like, man, Tom's 11:30 p.m. brain is actually cooked. He has no idea what he's talking about. But I think it should go something like this. So, oh gosh, my brain's really failing me. We want to compile, well, yeah, we want to compile all functions, right? One A. Func calls use deferred labels. But we know how big the body of each function is. Then actually let's also say 1b, all statics are defined. Because in compiling all the functions, we end up handling all of our static data. Then step 2, we go through each function definition again. We do another pass. And for each function, we look at the size of the... We calculate where it goes. We calculate where to put it in RAM, and based on the size of globals / statics, which we calculate up in 1b, right? So as part of compiling a function, step 0 is function declarations, right? We declare all functions ahead of time. That's step 0. This is why we don't need headers. So this is a checklist for how to actually fix this. I feel like we did a lot of good things, right? I laid the groundwork for actually dealing with static data. Maybe next stream I need to finally make a binary format as well. I feel like that also solves some of these problems. And it reduces the complexity of what I need to hand back from the compiler to anything consuming the compiler. If the compiler just gives back data in a known binary format, and I also provide, even in my WASM blob, parsers for that binary format and a loader for that binary format, like a function that just says, load this into the VM, it's a binary, that'd be cool. I want the binary format to be fairly simple. I'm not going to go full ELF, but it would be nice if it had some room for debug symbols. Maybe that's too far as well, I don't know. But debugging is really useful and really cool, and especially in the web view. Especially, the whole point I'm kind of, not so much of this, but if I want to start thinking about running this in WASM, the whole point is the web browser experience. And I think a binary format will really help. So I think that's a good goal for next time. We started this. We made progress on this. We started it. It didn't really pan out. So this has been a fun little stream. Bit low energy, bit chill. It's August now somehow, and we're going to keep smashing on. I did a lot of streams last month, and I hope I can do just as many this month, if not more. So, my name's Tom. It's been a lot of fun. We've made some good progress on strings today. Not quite as much as I hoped. We're getting there. We're closing in. I will be back tomorrow with much more exciting Rust compiler action, or maybe some other fun stuff. We'll see what happens. Thank you all so much for tuning in. Thank you everyone who's watching on YouTube, and I will catch you all next time.